how to design an RF filter that can operate for RF frequencies using lumped LC components only. So the filters are reflective in nature, that is, they're going to theoretically provide a perfect match between the load and source impedance in the passband, while they're going to keep the power off from reaching the load in the transition or stop band. Okay, so the filter design that we are concerned will be consisting of LC components only. Okay, so they are inherently lossless networks, right? So these are all the LC networks placed between the source impedance and the load impedance, right? Now, the other thing is that the response of the filter, well, it can be Butterworth. Okay, that is, it can have a monotonic response in both. It can have a monotonically decreasing frequency response in the transition band and flat response in the pass band. So, well, it can have Chebyshev response as well, having ripples in the pass band or in the stop band, if it is type 1 or type 2, or elliptic if it has ripples in both pass band and stop bands. So the response could be based upon any well-known classical analog filters. This kind of topology of circuit is that of a low-pass filter. Okay, this corresponds to the low-pass filter. Why it's a low-pass filter? Because you can see now for frequencies near around DC at 0, the inductive reactance is 0. Okay, so this becomes a short circuit. This is short circuit. Capacitors are open. So you have the maximum signal transmission between the source and the load. Okay, so this is your load, and between the source and load, the match is lossless. Okay, there is no impedance between the source and load if you're going to supply energy at very low frequencies. Okay, so this is going to favor low frequencies to pass through without much attenuation. But if the frequencies become high, then the inductances are going to pick up the impedance. Okay, they're going to beat the signal. Okay, while the capacitive susceptance is going to increase as well. That means capacitors are now going to act as short circuits, while inductors become open circuits. So you don't have any signal transmission. Okay, it's a low pass filter. Now, one thing before we get into the design is that you have to start the design by coming up with a prototype low pass filter. You have to come up with a design of a prototype low pass filter. What does it mean by a prototype low pass filter? Well, it's a low pass filter, but it has if it is a Butterworth filter, you can say it's a cutoff frequency, which is the half power point or the 3 dB point. So, for example, if it is V out, let's say, versus frequency, that's the output frequency response versus frequency. So the 3 dB point is where the response falls to 3 decibels less than below 0 decibels. Okay, and we call this as the cutoff frequency, and this happens with the bandwidth of the filter, so the pass band. Okay, and the stop band can start as specified at any frequency above the cutoff. Okay, this cutoff frequency in Butterworth filter might not be the edge of the pass band. Okay, the pass band edge could be, for example, could be specified in filter specifications, could be around -2 decibels, for example, or -1 dBs. Okay, so this point could be -2 decibels. So the pass band edge is not necessarily equal to the cutoff frequency. Okay, so this is your FP's pass band edge. Then you have the stop band edge. So these are filter specifications. Then you have the pass band tolerance. That, okay, in the pass band the response should not fall below -2 decibels. In stop band, let's say the response is to be at least -10 dBs. Okay, it's better if it is like -15 decibels or so on, but it can't be -9 dBs. Okay, so at least the attenuation should be -10 dBs, right? These are the filter specifications which, as a filter designer, you have to meet. Okay, in order to satisfy those requirements. Okay, so what does it mean by a prototype is that your passband edge will be, which is not necessarily equal to the cutoff frequency in Butterworth response, will be 1 radians per second if it is angular frequency, or it will be equal to, identically, this will be this is identically equal to 1 over 2 pi hertz, which is about 0.159 hertz. Okay, so this is 1 over 2 pi hertz. So you're going to design a prototype low pass filter. Even if you have to design a high pass filter or any other kind of band pass or band stop filter, other kind of frequency responses, you can start off with a prototype low pass filter, and that can be transformed to any desired response using simple frequency transformations. Okay, so what we are going to do is we are going to, first of all, your aim is to design the filter for 1 radians per second. Okay, that is your cutoff. Okay, and then your stop band edge, it can start from anywhere. Okay, it can be omega s. So it's angular frequency scale. Then your vertical scale could be either magnitude or in dBs. Okay, depends on the specifications, how they're specified. It can be converted from one form to another. So depending on the specifications, you start off with the prototype low pass filter. Okay, and then you can transform it to any other kind of filter. So this is what we are going to aim for. So let's have a look at some problems. These problems are from John B. Hagen, Radio Frequency Electronics, Circuits and Applications, 2nd edition. I'm going to put a link of the textbook in the description. So what the question says is, let's go through these problems, and then you'll understand how you'll get a feel of how these RF filters are designed. Okay, so the question is, design a 5-element low-pass filter having a Chebyshev response of 0.5 dB ripple shape, and the input and output impedances, they should be 100 ohms. Okay, so we have to use a parallel capacitors at the ends, and well, this is the circuit specification. The bandwidth from DC to the last 0.5 dB point is 100 kilohertz. Okay, now what it means is that it's not a Butterworth filter, so it's not going to be flat in the pass band. It's going to consist of some ripples like this. Okay, and the last ripple will where it occurs, so where it falls to about 0.5 dBs. Okay, so this last ripple, which is going to fall at 0.5 dBs. If this is 0, okay, let's consider this as 0. Then my ripple is going to, the last ripple where it falls to minus 0.5 dB. So this bandwidth is specified as that of bandwidth of a low pass filter or the pass band edge, and this should be how much? This should be about 100 kilohertz. Okay, so if this scale is 100, if this scale is in kilohertz, well, then this should be 100 kilohertz. Okay, so this is the specification for the pass band, and the input output impedances are 100, as you can see. Okay, and the circuit is going to consist of shunt capacitors at both the source and the load end. Okay, C1. This is C1, C3, and well, let's call this as C2. Never mind. So you have to use the table which is given in the appendix of the book. That is 4.2 to find the values of the prototype 1 ohm, 1 radians per second filter, and then alter these values for 100 ohms and 100 kilohertz. Well, what it means is that you have to start with the prototype low pass filter again, having the pass band edge is 1 radians per second. Also, the load and source impedances have to be 1 ohm instead of 100 ohms. Okay, and then we can alter the values. That is, for example, if the load and source are scaled by 100, your inductive reactance is also going to be scaled by 100. Okay, the capacitive reactances are going to be divided by 100 similarly. Okay, this is because 1 over j omega c, and then you have to denormalize the scale as well. Okay, so the 1 radians per second gets transformed. This pass band edge gets transformed to 100 kilohertz. So let's see how it is done. Now this is the table A 4.2, and this is taken from this table also appears in the appendix of the 4th chapter of John B. Hagen, and this consists of element values for Chebyshev low pass filters. This is for NdB ripple. The last NdB point is at 1 radian per second. So these values are for normalized low pass filter, or the prototype low pass filter, and the last NdB, whatever it is, 0.5 dB or 0.1 dB. The last NdB occurs at 1 radians per second, so that specifies the pass band edge. Okay, so in the question we are concerned with the 0.5 dB ripple. So this is where we have to start looking at, right? So I was telling that this table is taken from. This is the cited reference. This is Matthaei, Young, and Jones. So this is from Microwave Filters, Impedance Matching Networks, and Coupling Structures. This is the New York McGraw Hill publication 64, which is reprinted in 1980. Okay, so these tables can also be you can follow these tables in any classical analog filter literature, design books. Okay, so it brings some simplicity into the design, that you don't have to work out the poles and zeros on the Laplace Argand's diagram to satisfy the frequency specifications. You don't need to bother about those things and satisfy the given the transfer functions for the given specifications. Just have a look at what is required and how many, what is the order of the filter. So if, for example, the order of the filter, for example, this is, let's call this an N section filter. It simply means, according to the table, that how many inductors and capacitors are there. So for example, you have 1, 2, 3, 4, and 5. So you have 5 inductors plus capacitors. This is a 5-section Chebyshev filter. This is going to be a 5-section low-pass Chebyshev filter. Okay. So what we are going to do is we are going to look at a 5-section. We have 5 elements. So we are going to look at 5 elements. Table for 0.5 dB Chebyshev low-pass filter. Okay, this is 0.5 dB section. So let's consider these values. This is 1.7058, and then 1.2296, 2.54, and then again the values repeat on the other hand. Now what these values are and how to fit them into the lump components. So in appendix 4.1, which precedes 4.2, we have the component values for normalized low-pass filters. So you see this configuration, these two configurations are the same. They both are low-pass filters. Okay, I mean at DC you can see the transmission from the source to load is perfect, right? Because the inductors are again short-circuited and the capacitors are open-circuited. All right, you can have any of these. So any of these configuration topologies for low-pass filters. So now we are considering, since the requirement is to have shunt capacitors, let's consider this the topology of figure A, and you can see that if you compare these tables, now you have the values. Okay, so this is first of all you have to determine the value of N, how many lumped inductors and capacitors you require. So in this in the circuit configuration we require 5 elements, right? This is a 5 element. So we have 5 inductors and capacitors. Okay, this is determined. Then once the value of N is determined, okay, then we know this is 0.5 dB. So we have the value of N. Then comes the values of the LC components. So starting with G1, we have G1 as 1.7058. Okay, then G2 is 1.2296. Okay, and these values continue. So what is G1 and G2? Well, this is G1. So you for a normalized filter, for the normalized low-pass filter, my first capacitance is going to be 1.7058 farads, right? So this is 1.7058 farads, and then comes the series inductor, which is going to 12296 henries, and then 2.5408 farads. Again, the shunt capacitor, okay, the middle shunt capacitor, and then this continues, and you get to know that G5, the last lumped component, is how much? It's again 1.7058 farads. So I'm going to have this C2 as 1.7058 farads before the load comes. And for the normalized low-pass filter, you recall that this is again 1. Okay, this has to be scaled. So let's first construct this low-pass filter and try to simulate this in ADS. So I have the circuit schematic setup. I have these values taken from the table. So you can see these the shunt capacitors at the source and at the load, they are the same. Okay, and then in between we have the same series inductors. Okay, and the capacitor, the middle shunt capacitor, is about 2.5408 farads. These values are taken up from the table directly. Okay, and these are going to guarantee a 0.5 dB ripple normalized low-pass filter response. Let's see if we simulate this from let's say 0 to 1 megahertz with the normalized source and load resistances of 1 ohms. Okay, so the frequency is being swept from 0 to 1 hertz, because we know that what we are going to expect is that we're going to have the 0.5 dB ripple at 1 over 2 pi, or what is this, 0.159, around 0.16 hertz is your half. It's not the half dB, but where the last 0.5 dB ripple occurs. Okay, let me put this on. So this is the point where we are going to get 0.5 dB, the last 0.5 dB ripple. Okay, 0.5 dB ripple. Well, why I'm saying this is that because this is what the table says. So let's see. So the table says these are the element values for Chebyshev low pass filter. For a filter with n dB ripple, the last n dB point is at 1 radians per second, or 1 over 2 pi hertz. Okay. All right. So let's see. Now this is the simulatory response. The horizontal is the frequency scale in millihertz. So just we have to. This is 0.5 hertz. This is DC. And well, what I've done is that, okay, if you read this node V out, I'm considering the power. Okay, so this is the power V out, and V out square divided by 1. Okay, V out is over here. What I'm doing is I'm plotting the power response. So power response is, you can see it's V out squared, and well, you have to normalize this 1, so it doesn't matter. But the maximum value turns out to be about 0.25, with which it is normalized. So on the vertical scale, you have a normalized power response. Okay, so you can read the entire thing as a normalized power response. So let's say this is P and of F, normalized power response. Why it's normalized? Because it has been normalized with the maximum value. So it starts with 1. Well, it's not in dBs, but you should be able to see that the last ripple. Okay, I mean, you can expect that this is occurring at because this value is 0 dBs. Okay, and well, let's see how things they set in, because if you're going to, you have to convert this scale to in dBs. Well, this corresponds to 0 decibels, right? This is 0 decibels in power, and then you take 10 logarithm because this is power. So this point, I suspect, is 0.9, right? I mean, this is about 0.9. This is about 0.9. If you take the logarithm, well, this is equivalent to about minus 0.46 dBs. I mean, roughly, I'm just evaluating this because the scale has not been set to dBs, anyways. But you can appreciate that this point is again coming down to about. Let's take this down. So this point will be about 159 millihertz, which is about, again, the same 0.159 hertz, or 1 over 2 pi hertz, right? So this is the point. So we have realized the point, right? This is again 1 over 2 pi hertz. So this is the point where the last 0.5 dB ripple occurs. Okay, and now you can also see that where this point where the marker is set. This is the half power point, right? So for Chebyshev response, the half power point is not the 3 dB point. Well, yes, it is a 3 dB point. I mean, yes, but it's different. The response is different from Butterworth, where the cutoff frequency is usually taken to be equal to the 3 dB point. For Chebyshev, the passband edge is different. The passband edge is where the last tolerance of ripple occurs. So the tolerance was 0.5 dBs at and this occurs at around 159 millihertz, okay, approximately. So the half power transmission is occurring at a little more than that. That is 168.6 millihertz. Okay, that's where the about half of the energy of the power is transmitted. So it's a low pass filter, but it's a normalized low pass filter. Now, if you recall the question, well, the question was to have the passband edge denormalized to 100 kilohertz. Okay. And we also have to denormalize the load and the source resistance is 200 ohms. Okay, so how we are going to do that? Well, in the circuit, if you have to multiply this with 100, you have to scale this by 100 ohms, and you have to scale the load impedance by 100 ohms. So it becomes a scaling problem, right? Similarly, what we are going to do is, if this is my inductance, I have to scale this by 100 as well, right? So let's do this. You have to scale this by 100. Let's scale this by 100 as well. And for capacitor, well, they have to divide this by 100. Okay, because the capacitive reactance is the reciprocal. It's 1 over j omega c. They have to be divided. Okay, not here. Here, this has to be divided, and this has to be divided. So, well, this is your capacitances and inductances for scaled circuit. Well, not quite yet, because we also have to scale the frequency scale. In order to scale the frequency scale, we have to divide the entire thing with 2 pi into 100 kilohertz and you have to do this procedure with all the reactances. Okay, so for example, this is 1.705 divided by 100, and then you have to divide this with 2 pi divided by 100 kilohertz. And this procedure has to be carried out for all the lumped components. If you do that, these are the values that I'm getting. Okay, and now if you simulate this, the circuit with all these 5 LC values, with the impedances scaled to 100 ohms of the load and source, you see that this is an AC or linear circuit analysis done in ADS. Why? Because it consists of linear circuit elements. We don't have diode or transistors, and the frequencies start with 0 from DC and they go all the way to 400 kilohertz, because we expect the bandwidth of the low pass filter to be 100 kilos. So you can see, okay, this scale is in dBs. Okay, so this plot is alright. Now this M1 starts at minus 6.021 dBs. Now where does 0.5 dB, the last ripple, occurs? Well, this occurred at 100 kilowatt, and this is what we are looking for. Okay, you can see the scale has been denormalized, and this is the bandwidth. This is the bandwidth of the low pass filter. This is the point up until which we are going to transmit the signal with very less attenuation, right? And the frequency is also denormalized, right? So the bandwidth becomes 100 kilohertz, and as the frequency goes on increasing, the response falls off monotonically. There are no ripples in the transition band, neither there are any transition in the stop band. There are ripples, but they are hardly noticeable because the ripples are 0.5 dB, and on the scale 0.5 dB is highly discernible. This is a type 1 Chebyshev filter response, because the ripples are only occurring in the pass band. Okay, so you can see this is the procedure how to design a low pass filter. You have to start with the prototype low pass filter. This is a prototype low pass filter. Now this has the last n dB ripple occurring at 1/2 pi radians, 1/2 pi hertz. Okay, which defines the pass band edge of a normalized low pass filter. This can be denormalized by dividing the reactances by whatever is the desired pass band edge tolerance, pass band edge frequency. Okay, and you have to scale the reactances by the same factor by which your the load and the source impedance have been scaled. Okay, so you have to start with the normalized low pass filter. For example, this is normalized low pass filter schematic, having 1 ohm load, 1 ohm source and load. Okay, and then these have to be scaled. Okay, once you scale them, you have to scale the lumped components as well. Okay, with the same scaling factor. Then you have to divide them by the we have to denormalize the frequency scale as well. So we have to divide by the cutoff frequencies. Okay, in order to get a denormalized frequency scale. Okay, so once you get the circuit like this, you can simulate and just check the response, and you will have the desired performance of the filter. Okay, so that's all for the designing of low pass filters. Okay.